Hey, my friend. Tonight we're drifting through the biggest unanswered questions in astrophysics. Mysteries about the universe that science still can't fully explain. Just listen, relax, and let the vastness of space slowly carry you towards sleep. Chapter 1. What set the initial conditions of the universe? When astrophysics describes the universe, it usually begins with expansion, cooling, structure formation, and the gradual emergence of galaxies, stars, and planets. These processes are described with remarkable precision and are supported by a vast body of observational evidence. Yet beneath all of this success lies a deeper and quieter question. One that does not concern how the universe evolved, but why it began in the particular state from which all evolution followed. This question is known as the problem of the initial conditions of the universe. At its core, the problem asks why the universe started out so smooth, so uniform, and so extraordinarily ordered. Observations show that, at early times, matter and energy were distributed almost evenly across space, with only tiny irregularities. These small irregularities later grew into galaxies and large-scale cosmic structure, but their initial amplitude was astonishingly small. From the perspective of thermodynamics, such a state corresponds to extremely low entropy. In everyday physical systems, low entropy states are rare and unstable. They require explanation, preparation, or constraint. Yet the universe appears to have begun precisely in such a special configuration. Modern cosmology describes the evolution of the universe using general relativity combined with well-tested models of matter and radiation. When these equations are applied backward in time, they lead toward a hot, dense early state. However, the equations themselves do not specify why the universe began with the particular geometry, energy distribution, and entropy it had. They simply evolve whatever initial conditions are supplied. In this sense, the laws of physics describe motion, not origin. The choice of initial conditions remains external to the theory. One way to appreciate the depth of this problem is to consider entropy. Entropy is a measure of disorder, or more precisely, the number of microscopic configurations compatible with a given macroscopic state. In most physical systems, entropy tends to increase over time, a behavior known as the arrow of time. The universe clearly exhibits such an arrow. Stars burn fuel, structures form and decay, and energy spreads out. All of this is consistent with increasing entropy. However, the arrow of time itself depends on the universe starting in a very low entropy state. If the universe had begun in a high entropy configuration, there would be no clear direction of time as we experience it. What makes the early universe puzzling is not that it was hot or dense, but that it was smooth. A uniform distribution of matter in an expanding universe is actually a very special condition. Gravity naturally amplifies irregularities. A clumpy universe has far more possible microscopic arrangements than a smooth one. From this perspective, a uniform early universe is highly ordered and statistically unlikely. Yet this is precisely what observations reveal. Some cosmological models attempt to address this issue through the idea of cosmic inflation. Inflation proposes that, very early in cosmic history, the universe underwent a brief period of extremely rapid expansion. This expansion could stretch small regions of space into much larger ones, smoothing out irregularities and explaining the observed uniformity. Inflation also offers a mechanism for generating the tiny fluctuations seen in the cosmic microwave background, which later became galaxies and clusters. However, inflation does not fully solve the problem of initial conditions. It shifts the question rather than eliminates it. Inflation itself requires specific starting conditions to begin. The inflating region must already possess particular properties for the process to occur. Moreover, inflation does not explain why the universe began in a low entropy state in the first place. In fact, some analyses suggest that inflation may require fine-tuned conditions of its own. Another approach involves the concept of the cosmological constant or vacuum energy. The energy associated with empty space appears to play a major role in cosmic dynamics. Yet, theoretical estimates of vacuum energy based on quantum field theory differ dramatically from observed values. This discrepancy is one of the largest known gaps between theory and observation in physics. While vacuum energy influences the expansion of the universe, it does not explain why space-time itself emerged with the particular structure and initial smoothness we observe. Some physicists explore the possibility that the universe's initial conditions are determined by deeper laws not yet discovered. In this view, what appear to be arbitrary starting values may actually follow inevitably from a more fundamental framework. Candidates for such a framework include approaches to quantum gravity, which seek to unify general relativity with quantum mechanics. However, these theories remain incomplete and untested at the scales relevant to the universe's origin. Other ideas suggest that the universe may not be unique. In multiverse scenarios, different regions of a larger cosmic structure could possess different initial conditions. In such a picture, our universe's special properties might simply reflect a selection effect. Only regions with sufficiently ordered beginnings could give rise to long-lived structures and observers. While this idea is logically consistent, it remains controversial because it is difficult to test observationally. Astrophysics relies on evidence, and regions beyond our observable universe may never be accessible. There are also proposals in which time itself emerges from a more fundamental timeless description. In these models, the notion of an initial condition becomes subtle. Instead of a universe beginning at a moment in time, the universe might be described as a whole, with time arising as an approximate concept within it. While mathematically intriguing, such ideas remain far from experimental confirmation and often rely on abstract assumptions. What makes the problem of initial conditions especially challenging is that it lies at the boundary between physics and philosophy. Astrophysics excels at explaining processes that unfold within time, guided by known laws. But the origin of those laws and the reason the universe obeys them in the first place may not be questions that physics alone can answer. Even if a future theory predicts a unique set of initial conditions, it would still leave open the question of why that theory, and not another, governs reality. Observational evidence places strong constraints on early universe conditions. Measurements of the cosmic microwave background, large-scale structure, and primordial element abundances all point to a universe that began hot, dense, and remarkably uniform. These observations are among the most precise in all of science. Yet they describe the state of the universe shortly after its beginning, not the origin itself. The earliest moments remain hidden behind a veil that current theories cannot penetrate. The problem is not one of ignorance due to lack of data alone. It is a structural limitation. No observation can access a time before space-time itself existed, if such a time even makes sense. In this way, the initial conditions of the universe represent a horizon not just in space, but in explanation. Astrophysics can approach it, describe its consequences, and constrain its possibilities, but may never fully cross it. Despite this, the question remains deeply meaningful. The fact that the universe began in a state capable of generating complexity, structure, and life is extraordinary. Whether this reflects deep necessity, chance, or something beyond current understanding is still unknown. What is clear is that the universe did not have to be this way. Slightly different initial conditions could have led to a cosmos devoid of stars, chemistry, or long-term structure. As the day fades and your thoughts begin to slow, this uncertainty does not need to feel unsettling. It can be gentle. The universe does not demand that we resolve every mystery. It simply unfolds, carrying with it questions as vast as its own expansion. You do not need to solve the origin of everything tonight. It is enough to rest within the quiet fact that the universe began somehow and that you are part of its continuing story. Let the unanswered questions remain where they belong, far beyond the present moment, while your mind settles into calm and the day quietly releases its hold. Chapter 2. What happened before the Big Bang? When people ask what happened before the Big Bang, they are often imagining the universe as an explosion occurring at a particular point in time, followed by a sequence of earlier moments stretching backward into some deeper past. From the perspective of modern astrophysics, this intuition is understandable, but misleading. The Big Bang is not an explosion in space. It is a description of the early state of space and time themselves. As a result, the question of what happened before it turns out to be one of the most subtle and difficult questions science has ever faced. In standard cosmological models, the Big Bang marks a boundary in our mathematical description of the universe. When the equations of general relativity are applied to an expanding cosmos and traced backward, densities and temperatures increase without bound, eventually reaching a point where the theory itself ceases to be reliable. This boundary is often referred to as a singularity, but it is important to understand what that term really means. A singularity does not necessarily represent a physical object or event. It signals the breakdown of the theory being used. In this case, general relativity stops providing meaningful predictions. Because time is a part of space-time, and space-time is described by general relativity, the breakdown of the theory at the Big Bang creates a profound conceptual problem. If the theory that defines time no longer applies, it becomes unclear whether the concept of before has any physical meaning. Asking what happened before the Big Bang may be similar to asking what lies north of the North Pole. The question assumes a direction that no longer exists within the framework being used. Astrophysical observations allow us to reconstruct the universe's history back to an extremely early phase. The cosmic microwave background provides a snapshot of the universe when it first became transparent to radiation. Observations of light element abundances reveal conditions during primordial nucleosynthesis. Large-scale structure traces the growth of tiny initial fluctuations. Yet all of these windows open only after the universe was already evolving. They do not reach the origin itself. As we approach earlier and earlier times, the energy scales involved become increasingly extreme. Eventually, quantum effects of gravity are expected to become important. At this point, general relativity, which treats space-time as a smooth continuum, must be replaced or supplemented by a quantum description. Such a theory of quantum gravity does not yet exist in a complete experimentally verified form. This is one of the central open problems of fundamental physics. Several theoretical frameworks attempt to describe conditions near the beginning of the universe. Some approaches suggest that space-time itself emerged from a quantum state that does not resemble classical space or time. In these models, the Big Bang is not a moment in time, but a transition from a quantum regime to a classical one. Time, as we experience it, may not exist on the most fundamental level. Other models propose that the universe underwent a bounce rather than a beginning. In such scenarios, a previous contracting phase reached a minimum size and then transitioned into expansion. While mathematically possible within certain theoretical constructions, these ideas face significant challenges. They must reproduce the observed smoothness of the universe and avoid instabilities that would disrupt the transition. At present, there is no observational evidence that clearly favors a bounce over a beginning. There are also models in which the universe is eternal in some sense, even if the observable expansion is not. Some versions of inflation suggest that inflationary expansion may continue indefinitely in some regions while ending locally in others. In this picture, what we call the Big Bang would correspond to the end of inflation in our region, rather than the absolute beginning of everything. However, even these models often require an initial condition of their own. The question of ultimate origin is postponed, not eliminated. A key difficulty in all these ideas is testability. Astrophysics is an observational science. Its strength lies in its ability to compare theoretical predictions with measurable data. The earliest moments of the universe, if they involve physics beyond current theories, may leave only subtle or indirect signatures. Disentangling these from other effects is extraordinarily difficult. As a result, many proposals about what preceded the Big Bang remain speculative. It is also worth emphasizing that the concept of time itself may not be fundamental. In quantum physics, time plays a different role than it does in classical mechanics. Some approaches to quantum gravity suggest that time emerges from correlations between physical systems rather than existing as an independent backdrop. If this is the case, then asking what happened before time emerged may be fundamentally ill-posed. There may simply be no meaningful answer, not because of ignorance, but because the question does not correspond to a physical reality. Importantly, not knowing what happened before the Big Bang does not diminish what we do know. The success of modern cosmology in describing the universe's evolution is extraordinary. The expansion of space, the formation of galaxies, and the synthesis of elements are understood with remarkable precision. The unknown lies not in the everyday functioning of the universe, but at its deepest foundations. There is also a distinction to be made between unknown and unknowable. Some questions are unanswered simply because we lack sufficient data or computational power. Others may be inaccessible in principle, constrained by the structure of physical law itself. The question of what happened before the Big Bang may belong to the latter category. If time begins with the universe, then there is no earlier state to describe. In that case, the absence of an answer is not a failure of science, but a reflection of reality. Astrophysics continues to explore the earliest moments that can be meaningfully discussed. Observations of primordial gravitational waves, if detected, could offer new insights into very early cosmic dynamics. Precision measurements of cosmic background radiation may reveal subtle clues about processes that occurred long before stars formed. Yet even these advances may stop short of revealing an ultimate origin. As the universe expands and cools, it carries the imprint of its earliest moments, but not necessarily their cause. The Big Bang remains a boundary where our theories converge and then fall silent. Beyond it lies either a deeper level of physical description or the end of description altogether. As you reflect on this, it may help to notice that uncertainty does not imply emptiness. The absence of a clear before does not make the universe less meaningful. It simply means that existence may not follow the narratives we instinctively expect. The universe does not owe us an origin story that fits comfortably into human intuition. As the day settles and your thoughts begin to slow, you can allow this question to rest where it naturally belongs, at the edge of understanding. You do not need to resolve what came before everything. It is enough to exist within what is here now, in a universe that emerged somehow and continues quietly forward. The unanswered past does not disturb the present moment. It simply fades into the background, leaving space for rest, reflection, and calm. Chapter 3. What is dark matter made of? Among all the unresolved questions in astrophysics, dark matter occupies a unique position. It is not a speculative idea proposed to fill a gap in imagination, nor a distant phenomenon inferred from a single observation. Dark matter is woven deeply into almost every scale of cosmic structure we can measure. Galaxies rotate as if it exists. Clusters of galaxies bend light as if it exists. The large-scale architecture of the universe grows and evolves as if it exists. And yet, despite decades of careful study, no one knows what dark matter is actually made of. The story of dark matter begins with motion. When astronomers measure how stars orbit within galaxies, they find something unexpected. The outer regions of galaxies rotate much faster than they should if gravity were produced only by visible matter such as stars, gas, and dust. According to well-tested gravitational laws, these outer stars should move more slowly or even drift away. Instead, their speeds remain nearly constant far from galactic centers. The simplest explanation is that galaxies are embedded in vast halos of unseen mass that exert additional gravitational pull. This conclusion does not depend on one galaxy or one method. It appears consistently across spiral galaxies, elliptical galaxies, and dwarf galaxies. The same pattern emerges when examining galaxy clusters, where the motions of individual galaxies suggest far more mass than can be accounted for by luminous matter alone. Even hot gas trapped within clusters emits X-rays that reveal gravitational confinement by something invisible. Perhaps the most striking evidence comes from gravitational lensing, an effect predicted by general relativity and confirmed many times over. Massive objects warp space-time, bending the paths of light passing nearby. When astronomers observe distant galaxies whose light passes through clusters of galaxies, they see distortions that map the underlying mass distribution. These maps consistently show far more mass than can be explained by visible matter. In some cases, such as collisions between galaxy clusters, the visible matter and the gravitational mass become spatially separated, strongly suggesting that the dominant mass component does not interact with light or normal matter in the usual way. Together, these observations form a coherent and overwhelming case that dark matter exists. It behaves gravitationally like matter, clustering and shaping cosmic structures, yet it neither emits nor absorbs light. It does not participate significantly in electromagnetic interactions. It passes through ordinary matter almost without effect. Whatever it is fundamentally different from the particles that make up stars, planets, and living beings. Importantly, dark matter is not simply ordinary matter hidden from view. Extensive searches for faint stars, cold gas, black holes, and other non-luminous objects show that they cannot account for the required mass. Big Bang nucleosynthesis, which predicts the abundances of light elements in the early universe, places strict limits on how much ordinary matter can exist. These limits are independently confirmed by observations of the cosmic microwave background. Together, they show that the majority of matter in the universe must be non-baryonic, meaning it is not composed of protons and neutrons. This realization shifts the problem from astronomy to fundamental physics. If dark matter is not made of known particles, then it must consist of something new. Many theoretical candidates have been proposed, motivated by extensions of particle physics beyond the standard model. Some hypothetical particles would interact extremely weakly with normal matter, making them difficult to detect directly. Others might have formed abundantly in the early universe and persisted until today. Despite intense experimental effort, no direct detection of dark matter particles has yet been confirmed. Highly sensitive underground detectors search for tiny signals produced when dark matter particles collide with atomic nuclei. Space-based instruments look for byproducts of dark matter annihilation or decay. Particle accelerators attempt to create dark matter in high-energy collisions. So far, all results remain inconclusive. Each null result narrows the range of possibilities, but none has yet revealed the true nature of dark matter. This absence of direct detection has prompted some researchers to question whether dark matter exists as a particle at all. Alternative theories propose modifications to gravity that could mimic the effects attributed to dark matter. These ideas attempt to explain galaxy rotation curves without invoking unseen mass. While such theories can reproduce certain galactic observations, they struggle to account simultaneously for the full range of evidence, particularly on cosmological scales, and in systems where gravitational lensing clearly indicates additional mass separate from visible matter. At present, dark matter remains the more comprehensive explanation. Cosmological observations further reinforce the dark matter picture. Measurements of the cosmic microwave background reveal tiny fluctuations in temperature that encode information about the universe's composition shortly after its early expansion phase. These patterns are consistent with a universe dominated by dark matter and dark energy, with ordinary matter forming only a small fraction of the total mass-energy content. Large-scale simulations that include dark matter successfully reproduce the web-like structure of galaxies observed across the universe. Without dark matter, these structures would not form in the time available. One of the most intriguing aspects of dark matter is its apparent passivity. It shapes the universe through gravity, yet it seems almost indifferent to everything else. It does not clump into stars. It does not cool by radiating energy. It forms diffuse halos rather than compact objects. In a sense, it provides the gravitational scaffolding upon which visible matter builds complexity, while remaining itself invisible and silent. This raises profound questions about the nature of matter and the completeness of our physical theories. The standard model of particle physics has been tested with extraordinary precision, yet it does not contain a suitable dark matter candidate. If dark matter exists as a new particle, it would represent the first confirmed form of matter beyond this framework. Such a discovery would reshape our understanding of the fundamental constituents of reality. At the same time, it is possible that dark matter is not a single substance, but a collective name for phenomena arising from deeper principles not yet understood. It may involve new symmetries, hidden dimensions, or unfamiliar interactions that only reveal themselves gravitationally. These ideas remain speculative, but they highlight how dark matter sits at the intersection of astrophysics and fundamental physics. What makes the dark matter problem especially compelling is its empirical grounding. This is not a mystery born of missing imagination, but of excess evidence. Everywhere we look, gravity behaves as if more matter is present than we can see. The universe itself seems to insist on the existence of something beyond our current catalog of particles. Yet even as dark matter dominates cosmic mass, it plays little direct role in everyday experience. It passes through Earth without notice. It flows through your body as you read or listen, exerting only a tiny gravitational influence. Its presence is vast on cosmic scales and negligible on human ones. This contrast between cosmic importance and local invisibility adds to its quiet strangeness. Dark matter also challenges intuition about what it means for something to exist. We are accustomed to identifying matter by its interactions, by the light it emits or reflects, by the forces we can feel. Dark matter resists all such familiar markers. It reveals itself only through the motion of other things. In this way, it is known entirely by its effects, not by its essence. As astrophysics continues to refine observations and experiments grow ever more sensitive, the hope remains that dark matter will eventually be identified. Perhaps a faint signal will emerge from a detector deep underground, or a subtle signature will appear in cosmic radiation. Or perhaps the solution will require a more radical shift in understanding. one that reframes gravity or matter itself. Until then, dark matter stands as a reminder that the universe is not obligated to conform to human expectations. Most of what exists does not announce itself. It simply shapes the world quietly, from behind the scenes, leaving traces that must be patiently interpreted. As you let this idea settle, it can offer a gentle perspective. The universe is filled with things that exist without being seen, forces that act without being felt, structures that support everything without drawing attention to themselves. Dark matter does not intrude. It does not rush. It simply is. And in that quiet presence, there is something calming. You are not required to see everything to be supported by it. Some of the most important parts of the universe work silently, allowing everything else to unfold at its own pace. Chapter 4. What is dark energy, really? At the largest scales we can observe, the universe is not merely expanding. It is expanding in a way that grows faster with time. Galaxies are not just moving away from one another because space itself stretches, but the rate of that stretching appears to be increasing. This unexpected behavior is attributed to something called dark energy, a term that captures both its profound influence and our deep ignorance of its nature. The discovery of accelerated cosmic expansion came as a surprise. For much of the 20th century, astronomers expected gravity to slow the expansion of the universe. Depending on the total amount of matter and energy present, the universe might expand forever at a decreasing rate, or eventually stop and recollapse. Instead, precise observations of distant stellar explosions revealed that the expansion has been speeding up over time. This finding reshaped modern cosmology and introduced one of the most significant unsolved problems in astrophysics. Dark energy is not observed directly. Its existence is inferred from the behavior of the universe as a whole. Measurements of distances to faraway galaxies, combined with observations of cosmic background radiation and large-scale structure, consistently indicate that some form of energy permeates space and exerts a repulsive gravitational effect. This effect becomes noticeable only over immense distances, where the cumulative influence of space itself dominates over local gravitational attraction. Unlike ordinary matter or even dark matter, dark energy does not appear to cluster. It does not gather into halos, stars, or galaxies. Instead, it seems to be distributed smoothly throughout space. As the universe expands and space increases, the influence of dark energy does not dilute in the same way matter does. This property is one of its most puzzling aspects, and one of the reasons it drives accelerated expansion. One of the simplest ways to describe dark energy within existing theories is through the concept of vacuum energy. In quantum physics, empty space is not truly empty. It contains fluctuating fields with associated energy. In principle, this vacuum energy should have gravitational effects. In cosmology, a constant vacuum energy corresponds mathematically to what is known as a cosmological constant. This idea was originally introduced into gravitational theory long before the discovery of cosmic acceleration, then discarded and later revived in a new context. While the cosmological constant provides an excellent fit to observational data, it introduces a severe theoretical problem. Calculations of vacuum energy based on quantum field theory predict values that are enormously larger than what is observed astronomically. The discrepancy between theoretical expectations and measured cosmic acceleration is among the largest known mismatches in all of physics. Explaining why vacuum energy appears so small yet non-zero remains an open challenge. Alternative ideas attempt to explain dark energy as something dynamic rather than constant. In these models, dark energy could arise from a field that evolves slowly over cosmic time, changing the rate of expansion in subtle ways. Such theories are constructed to match current observations, but they introduce new entities and parameters whose origins are not well understood. As of now, no dynamic model has been confirmed over the simpler constant explanation. Another possibility is that our understanding of gravity itself may be incomplete on the largest scales. General relativity has been tested extensively within the solar system and around compact objects like stars and black holes. However, cosmic acceleration occurs on scales far beyond these environments. Some theories propose that gravity behaves differently when averaged over vast distances, producing effects that mimic dark energy. These ideas are actively studied, but they must reproduce all existing observations with the same accuracy as standard cosmology, a demanding requirement. Observationally, dark energy dominates the current energy budget of the universe. Ordinary matter and dark matter together account for only a minority of the total. This dominance emerged relatively late in cosmic history. Early on, matter governed the expansion and allowed structures like galaxies to form. Only after space expanded sufficiently did dark energy become the primary driver of cosmic dynamics. This timing raises additional questions. Why does dark energy become important precisely during the era when observers like us exist? This coincidence has no widely accepted explanation. Unlike dark matter, which reveals itself through motion and structure formation, dark energy is known almost entirely through its influence on expansion. It does not leave localized signatures. It does not bend light in the same way matter does. It does not participate in familiar interactions. Its presence is inferred statistically through careful measurements of cosmic distances and expansion history. In this sense, dark energy is even more elusive than dark matter. Yet the evidence for it is remarkably consistent. Independent observational techniques converge on the same conclusion. The expansion of the universe is accelerating. Large surveys mapping the distribution of galaxies support this picture. Measurements of background radiation patterns reinforce it. The overall framework of modern cosmology, though incomplete in explanation, is internally coherent and strongly supported by data. The challenge lies not in describing what dark energy does, but in understanding what it is. Is it a property of space itself, inseparable from the fabric of the universe? Is it a new form of energy or field that fills all of space? Or is it a sign that gravity behaves differently on the largest scales imaginable? Each possibility carries profound implications for physics. If dark energy is vacuum energy, it connects the fate of the universe to the deepest aspects of quantum theory. If it is dynamic, it suggests the existence of new fields beyond those currently known. If it reflects modified gravity, it implies that our understanding of space-time is incomplete. In all cases, dark energy points toward physics beyond the established frameworks. The ultimate fate of the universe is closely tied to the nature of dark energy. If it remains constant, the universe will continue expanding, galaxies will drift farther apart, and distant regions will gradually disappear beyond observable horizons. If it changes over time, the future could be very different. Some hypothetical behaviors could slow expansion, while others could accelerate it dramatically. Current observations favor a stable scenario, but uncertainty remains. What makes dark energy especially unsettling is how little it interacts with the rest of reality. It does not shape galaxies directly. It does not influence chemistry or biology. It operates silently, steadily, altering the geometry of space on scales so vast they are difficult to imagine. It is a reminder that the universe is governed by influences that have no counterpart in daily experience. At the same time, dark energy demonstrates the power and limits of astrophysics. Through observation and inference, scientists have uncovered a dominant component of the cosmos that was completely unknown until recently. Yet naming it does not equate to understanding it. The term dark energy is a placeholder, a signpost marking a profound gap in knowledge. As research continues, future observations may reveal subtle deviations from current models. Improved measurements of cosmic expansion could hint at whether dark energy is truly constant or slowly evolving. New theoretical insights may bridge the gap between gravity and quantum physics, or the mystery may persist, reminding us that even with precise data, some aspects of nature resist simple explanation. As you reflect on this unseen force shaping the cosmos, it may help to remember that dark energy does not act with urgency. Its influence unfolds over immense spans of time. Nothing about it demands immediate resolution. The universe expands calmly, guided by laws that operate far beyond human concern. As the day draws to a close, you can allow this thought to settle gently. The universe is vast, and much of it works quietly, without drama or intention. Dark energy carries everything outward, slowly and steadily, without needing to be understood tonight. You can rest knowing that even the greatest mysteries move at a patient pace, leaving room for stillness, reflection, and sleep. Chapter 5. Why is the universe so uniform on large scales? When astronomers map the universe on its largest scales, a striking pattern emerges. No matter which direction we look, the universe appears broadly the same. Galaxies are distributed in a vast web of filaments and voids, but when averaged over immense distances, the overall properties of space look remarkably uniform. Temperatures, densities, and large-scale motions differ only slightly from place to place. This smoothness is not absolute, but it is precise enough to pose one of the deepest puzzles in astrophysics. This observed uniformity is often described as isotropy and homogeneity. Isotropy means that the universe looks similar in all directions. Homogeneity means that, on sufficiently large scales, it looks similar from different locations. Together, these properties form the foundation of modern cosmological models. They are not assumptions made lightly, but conclusions drawn from decades of increasingly precise observations. One of the strongest pieces of evidence for large-scale uniformity comes from the cosmic microwave background. This faint radiation fills all of space and represents a snapshot of the universe when it was very young. Measurements show that its temperature is almost identical in every direction, with only tiny variations. These variations are real and significant, but their small size emphasizes how smooth the early universe was. What makes this surprising is the finite speed at which information travels. Light, and any influence governed by physical laws, moves at a limited speed. In the early universe, distant regions were separated by distances so large that there was not enough time for light or any signal to pass between them. According to standard expansion models, these regions were causally disconnected. They could not have exchanged energy or information, yet they ended up with nearly identical properties. This tension between observed uniformity and limited causal contact is known as the horizon problem. It highlights a conflict between what the universe looks like and what standard physical processes would allow. If different regions could not communicate, why do they appear to have coordinated their temperatures and densities so precisely? One proposed resolution involves a period of extremely rapid expansion very early in cosmic history. In this picture, regions that are now far apart were once much closer together and able to reach equilibrium before being stretched beyond each other's horizons. This idea can account for the observed smoothness while preserving known physical laws. It also explains why small fluctuations exist and why they have specific statistical properties. However, while this mechanism explains many features of the universe, it introduces new questions of its own. It requires particular conditions to begin and does not by itself explain why those conditions were present. Moreover, it predicts a universe that is extremely uniform, but not perfectly so. The precise pattern of deviations remains an area of active study. Beyond the early universe, uniformity persists even as structures form. Galaxies cluster under gravity, creating filaments, walls, and voids. On smaller scales, the universe is highly structured and irregular. Yet when viewed across sufficiently vast distances, these structures average out. The result is a universe that is clumpy locally but smooth globally. Understanding how this transition occurs is a key achievement of modern cosmology, but it also emphasizes how finely balanced the initial conditions must have been. The laws governing cosmic expansion and structure formation amplify small irregularities over time. If the early universe had been too uneven, gravity would have exaggerated those differences, leading to a cosmos dominated by massive clumps and empty regions with little overall uniformity. If it had been perfectly uniform, no structures would ever have formed. The observed universe lies delicately between these extremes. Large-scale uniformity also appears in the expansion itself. Measurements of how galaxies move away from one another show that expansion proceeds at nearly the same rate in all directions. Deviations exist due to local gravitational effects, but when averaged over large distances, the expansion is remarkably even. This behavior supports the idea that space itself has no preferred direction or location on cosmic scales. From a theoretical standpoint, this uniformity simplifies cosmological modeling. It allows astrophysicists to describe the universe using relatively simple equations that capture its overall behavior. Yet the simplicity of the description contrasts with the difficulty of explaining why the universe satisfies these conditions at all. Some researchers have explored whether uniformity could arise naturally from generic initial states. In these approaches, the expansion of space itself acts to smooth out irregularities over time. However, this smoothing is limited. Certain kinds of inhomogeneities grow rather than shrink. The degree of uniformity observed still points to a special early state. Another line of inquiry examines whether our observations might be biased by our location. Perhaps we inhabit a region that appears uniform, while the universe as a whole is more varied. While this idea cannot be ruled out completely, extensive surveys of galaxies and background radiation suggest that uniformity extends far beyond the regions we directly sample. No compelling evidence has been found for large-scale departures from this pattern. Uniformity also connects to deeper questions about the nature of physical law. The same fundamental constants and interactions appear to operate throughout the observable universe. Spectral lines from distant galaxies show the same atomic behavior as those measured on Earth. This consistency reinforces the idea that the universe is not only geometrically uniform, but governed by the same rules everywhere we can see. Despite these observations, uniformity remains puzzling because it seems to require explanation rather than assumption. Astrophysics can describe how uniformity evolves, how it is perturbed, and how it manifests in data. Explaining why it exists at all may require insight into physics at energies and conditions far beyond current experiments. It is also possible that uniformity is not absolute, but approximate. Tiny deviations exist and may hold clues to deeper processes. Precise measurements continue to test whether the universe is truly isotropic or whether subtle patterns betray a more complex origin. So far, the simplest picture remains consistent with observations, but future data may reveal surprises. The question of uniformity ultimately intersects with the question of cosmic origin. The early universe appears to have been prepared in a way that allowed both large-scale smoothness and small-scale structure. This balance enabled the formation of galaxies, stars, planets, and eventually life. Whether this balance is the result of necessity, chance, or deeper law is still unknown. What is clear is that uniformity is not trivial. It is not the default outcome of arbitrary beginnings. It reflects a universe that began in a remarkably specific state, one that continues to shape everything that followed. As the universe expands, its large-scale uniformity becomes more pronounced. Distant regions move farther apart, and local structures become increasingly isolated. Over immense spans of time, the universe may appear smoother and emptier, even as complexity persists in small pockets. This quiet trend toward large-scale simplicity contrasts with the richness of local experience. As you reflect on this, it may be comforting to realize that the same uniformity that puzzles astrophysicists also provides stability. The universe does not tear itself apart with wild asymmetries. It unfolds gently, governed by patterns that repeat across unimaginable distances. As the day releases its hold, you can let your thoughts drift across this vast smoothness. The universe is wide, even, and patient. It does not rush or demand attention. It simply extends in all directions, steady steady and calm, offering a sense of quiet order in which the mind can rest. Chapter 6. What happens inside a black hole? Black holes are among the most extreme objects predicted by astrophysics, and they occupy a unique place in our understanding of the universe. They are not exotic in the sense of being rare curiosities. On the contrary, observations indicate that black holes are common, forming from the collapse of massive stars and residing at the centers of most large galaxies. Their existence is well supported by multiple lines of evidence. Yet despite this confidence, what actually happens inside a black hole remains one of the deepest unsolved questions in science. From the outside, black holes are described with remarkable simplicity. According to general relativity, an isolated black hole can be fully characterized by only a few properties, such as its mass and rotation. These quantities determine how the black hole influences its surroundings, how it bends light, and how nearby matter moves. Astrophysicists can model the orbits of stars near galactic centers, observe disks of hot gas spiraling inward, and even image the shadow cast by a black hole against glowing material behind it. All of this lies outside the black hole itself, in the region where space-time remains accessible to observation. The boundary that separates what we can observe from what we cannot is known as the event horizon. This surface is not a physical barrier in the usual sense. It is a geometric boundary in space-time. Once an object crosses it, all possible future paths lead deeper inward. No signal, no matter how fast or energetic, can escape back to the outside universe. For distant observers, the event horizon represents a point of no return. The physics outside the event horizon is well understood and extensively tested. The physics inside is where certainty ends. General relativity predicts that within the horizon, space-time becomes so strongly curved that all trajectories lead toward a central region, often called a singularity. At this location, densities and space-time curvature grow without bound in the mathematical description. However, as with the origin of the universe, the appearance of a singularity signals the breakdown of the theory, not necessarily the presence of a physically infinite object. Inside the event horizon, the roles of space and time become profoundly altered. Directions that once corresponded to spatial movement now behave like time. Moving inward is no longer a choice. It is as inevitable as moving forward in time. This reversal of structure makes it impossible to construct stable configurations or halt the inward progression. From the perspective of classical general relativity, once inside, the singularity lies in the future, not merely in a particular location. Yet general relativity is a classical theory. It does not incorporate quantum effects, which are known to dominate at extremely small scales and high energies. Near the central regions of a black hole, quantum effects are expected to become significant, possibly overwhelming the classical description. Unfortunately, there is no complete theory that successfully unifies gravity with quantum mechanics. As a result, predictions about the true interior of a black hole remain speculative. Some approaches to quantum gravity suggest that the classical singularity may be replaced by something else entirely. Instead of infinite density, space-time might reach a highly compressed but finite state. In these models, The interior of a black hole could involve exotic phases of space-time, unfamiliar geometries, or quantum structures with no classical counterpart. While mathematically consistent in certain frameworks, these ideas have not yet been confirmed or ruled out by observation. One of the most important insights into black hole interiors comes indirectly from the study of black hole thermodynamics. Black holes possess temperature and entropy, properties normally associated with ordinary matter. This realization implies that black holes have microscopic degrees of freedom, even though classical descriptions treat them as simple geometric objects. Understanding what these degrees of freedom represent may offer clues about the true nature of the interior. Quantum field theory applied near the event horizon predicts that black holes are not entirely black. They emit a faint radiation due to quantum effects in curved spacetime. Over extremely long periods, this radiation would cause black holes to lose mass. While this phenomenon occurs primarily at the horizon rather than deep inside, it highlights the necessity of combining quantum physics with gravity when describing black holes. This leads to a profound paradox. If a black hole eventually evaporates, what happens to the information carried by the matter that fell inside? Classical physics suggests that information is destroyed at the singularity. Quantum physics insists that information must be preserved. Reconciling these principles requires a deeper understanding of what happens inside the black hole and how the interior relates to the exterior. Some theoretical ideas propose that information is encoded at the event horizon itself, rather than stored in the interior in the usual sense. In these pictures, the interior description may be redundant, an emergent concept rather than a fundamental one. Other approaches suggest that the interior remains real, but is described by quantum correlations that extend to the outside universe. These ideas are active areas of research, but none has yet achieved universal acceptance. From an observational standpoint, the interior of a black hole is fundamentally inaccessible. No signal from within the event horizon can reach an external observer. This limitation is not technological, but physical. It is built into the structure of space-time itself. Even a hypothetical observer falling into a black hole could not send information back once the horizon is crossed. This raises the possibility that some aspects of black holes may be unknowable in principle. Astrophysics relies on observation, inference, and testable prediction. If the interior of a black hole cannot influence anything outside, then it may be impossible to directly verify any detailed description of it. This does not mean that theories are meaningless, but it does place strong constraints on what can be confirmed. Despite this, black holes play a crucial role in the universe. They influence the formation and evolution of galaxies, regulate the growth of stars, and shape cosmic environments through powerful jets and radiation emitted by surrounding matter. The fact that their interiors are hidden does not diminish their importance. Instead, it highlights how much of reality operates beyond direct access. It is also worth noting that black holes challenge everyday intuitions about space, time, and causality. Inside a black hole, familiar concepts dissolve. Distance loses its usual meaning. Time cannot be paused or reversed. The future becomes a direction rather than a moment. These features are not philosophical embellishments. They follow directly from well-tested physical laws when pushed to their limits. The question of what happens inside a black hole therefore sits at the intersection of astrophysics, relativity, and quantum theory. It exposes the seams between our most successful frameworks. Each theory works extraordinarily well within its domain, yet neither is sufficient on its own to describe the extreme conditions inside a black hole. Progress may come from unexpected directions. Observations of gravitational waves produced by merging black holes test gravity in its strongest regime. Studies of quantum information theory have reshaped how physicists think about space-time and entropy. Advances in theoretical physics continue to explore new mathematical structures that could describe black hole interiors more accurately. For now, the interior of a black hole remains a region where our knowledge fades, not because of a lack of curiosity or effort, but because nature itself imposes boundaries. Black holes remind us that the universe contains places where explanation becomes tentative and where certainty gives way to possibility. As you sit with this idea, it can feel less threatening and more gentle. Not everything needs to be illuminated to be meaningful. The universe contains depths that remain dark, not out of neglect, but because they are woven into the fabric of reality itself. As the day quiets and your thoughts slow, you can allow those depths to remain where they are, vast and unseen. The black holes of the universe hold their secrets patiently, and you are free to rest, knowing that mystery does not demand resolution, only acceptance. Chapter 7. Does information really disappear? In physics, the concept of information has a precise and somewhat unfamiliar meaning. It does not refer to thoughts, memories, or messages, but to the complete description of a physical system. Information encodes the exact state of particles, their positions, motions, and quantum properties. In modern physics, information is not merely a bookkeeping tool. It is treated as something fundamental, governed by strict rules. One of the deepest of these rules is that information is never destroyed. And yet, when black holes enter the picture, this principle appears to be placed under extraordinary strain. The puzzle known as the black hole information problem arises from the collision of two pillars of modern physics. On one side stands quantum mechanics, which insists that the evolution of physical systems preserves information. Even when systems appear chaotic or disordered, the underlying quantum description retains a complete record of the past. On the other side stands general relativity, which predicts the formation of black holes with event horizons that permanently hide anything that falls inside. When these two frameworks are applied together, they seem to lead to incompatible conclusions. To understand the problem, imagine matter falling into a black hole. From the outside, we can track this matter as it approaches the event horizon. Its energy and momentum affect the black hole's mass and rotation, but its detailed internal structure appears to be lost. Once the matter crosses the horizon, it becomes causally disconnected from the rest of the universe. Classical descriptions suggest that the information carried by that matter continues inward and is ultimately destroyed at the singularity. If black holes were perfectly eternal, this loss might be tolerated as a peculiar but isolated feature of gravity. However, quantum effects complicate the picture. When quantum fields are considered in the curved space-time around a black hole, a subtle process emerges in which the black hole emits radiation. This radiation carries energy away, causing the black hole to slowly lose mass. Over extremely long periods, a black hole could evaporate completely. Here's where the contradiction sharpens. If a black hole forms from matter with a well-defined quantum state and then evaporates entirely into radiation that appears random, the final state seems to contain less information than the initial one. This would mean that information has been irretrievably lost from the universe. Such a process would violate a central principle of quantum theory and undermine its internal consistency. For many years, physicists debated whether this apparent loss of information was real or merely an artifact of incomplete understanding. Some argued that quantum mechanics might need to be modified in the presence of strong gravity. Others suspected that the calculations describing black hole radiation were missing subtle correlations that preserve information in ways not immediately obvious. A key insight came from the realization that radiation emitted by a black hole might not be perfectly random after all. While early radiation appears thermal and featureless, later radiation could carry increasingly subtle correlations that encode information about what fell into the black hole. In this view, information is not destroyed, but released extremely slowly and in a highly scrambled form. Recovering it would be practically impossible, but not forbidden in principle. This idea aligns with the broader understanding that information can be hidden without being destroyed. When a book is burned, the information in its text is not eliminated. It is dispersed into microscopic degrees of freedom in smoke, ash, and heat. In practice, it is unrecoverable, but in principle, it still exists. Black holes may represent an extreme version of this process, where information is not lost but becomes extraordinarily inaccessible. However, implementing this idea consistently within known physics has proven challenging. Calculations suggest that for information to escape, the region near the event horizon must behave in ways that differ from classical expectations. Some proposals suggest that the horizon itself plays an active role in storing and processing information, rather than acting as a passive boundary. One influential perspective treats the event horizon as a kind of information-rich surface with microscopic degrees of freedom proportional to its area. In this view, everything that falls into a black hole leaves an imprint on the horizon. The interior description becomes secondary or even redundant. The black hole's entropy reflects the vast number of possible microscopic configurations associated with this surface. This line of reasoning has led to the idea that space-time itself may be an emergent phenomenon arising from more fundamental quantum information processes. In such frameworks, the geometry of a black hole and the flow of information are deeply intertwined. The interior of the black hole may not be a separate region in the traditional sense, but a manifestation of quantum correlations encoded at the boundary. Yet these ideas raise further questions. If information is stored at the horizon, what happens to an observer who falls into the black hole? According to general relativity, that observer should experience nothing special at the horizon, at least for sufficiently large black holes. Reconciling this smooth experience with an information-rich horizon has led to intense debate. Some proposals suggest that the classical picture of a smooth horizon must break down at a fundamental level. Others attempt to preserve both perspectives through subtle consistency conditions. The difficulty lies in the fact that no single observer can access all aspects of the process. An external observer sees information encoded in radiation and horizon properties. An infalling observer experiences a seemingly ordinary crossing of the horizon. Both descriptions may be valid within their own frames, even if they cannot be combined into a single global picture. This challenges traditional notions of objective reality and forces physicists to rethink what it means for information to exist. Importantly, this problem is not confined to black holes alone. It touches on the nature of time, causality, and the limits of observation. Information is always defined relative to what can be measured and by whom. In extreme environments like black holes, these limitations become fundamental rather than practical. Over the years, progress has come from unexpected directions. Insights from quantum information theory, originally developed for studying computation and communication, have reshaped how physicists think about space-time and gravity. Concepts such as entanglement have emerged as central players in understanding how information might be preserved even when classical descriptions fail. Despite these advances, no single solution has achieved universal acceptance. Most physicists now believe that information is ultimately conserved, even in the presence of black holes. However, the precise mechanism by which this occurs remains unclear. The resolution likely requires a complete theory that unifies quantum mechanics and gravity, a goal that remains one of the grand challenges of modern physics. What makes the information problem especially profound is that it reveals a limit not just of knowledge, but of description. Our best theories each capture essential aspects of reality, yet they struggle to coexist under extreme conditions. Black holes expose these tensions with exceptional clarity. At the same time, this mystery highlights the coherence of the universe. The fact that information conservation is so deeply embedded in physical law suggests that reality is not arbitrary. Even when systems appear to erase the past, deeper structures may preserve it in ways that transcend intuition. As you reflect on this, it may help to step back from the technical details. Information, in the physical sense, is not fragile. It does not vanish easily. It transforms, disperses, and hides, but it endures. The universe carries its history forward, even when that history becomes impossible to read. As the day comes to rest, you do not need to follow every detail of this cosmic accounting. It is enough to know that nothing is simply erased. Experiences pass, moments dissolve, but traces remain woven into the unfolding fabric of time. Like information near a black hole, the day you have lived does not disappear. It settles quietly into the background, preserved in ways unseen, allowing your mind to release it and drift gently toward rest. Chapter 8. Why does the universe contain more matter than antimatter? One of the most fundamental questions in astrophysics is not about distant galaxies or exotic objects, but about existence itself. Why is there anything at all? According to our best understanding of fundamental physics, the early universe should have produced matter and antimatter in almost equal amounts. Matter and antimatter are mirror counterparts. For every particle of matter, there exists an antimatter partner with the same mass but opposite charge and quantum properties. When matter and antimatter meet, they annihilate, converting their mass entirely into energy. If the universe had begun with perfectly equal amounts of both, nearly all of it should have annihilated into radiation, leaving behind a cosmos filled with light, but devoid of stars, planets, and life. Yet that is not what we observe. The universe around us is overwhelmingly made of matter. Antimatter exists only fleetingly, produced in high-energy environments such as particle accelerators, cosmic ray interactions, or radioactive decays, and then quickly annihilated. This imbalance is tiny in absolute terms, but cosmically decisive. A minute excess of matter over antimatter in the early universe is responsible for everything we see today. Astrophysical observations confirm this imbalance on the largest scales. When matter and antimatter annihilate, they produce characteristic radiation. If large regions of the universe were composed of antimatter, we would observe intense annihilation signals at the boundaries between matter and antimatter domains. Extensive surveys of cosmic radiation show no evidence for such boundaries. Galaxies, clusters, and the diffuse gas between them all appear to be made of matter, not antimatter. The asymmetry is global. The puzzle deepens when we consider the early universe. At extremely high temperatures, energy converts readily into particle-antiparticle pairs. The early universe was hot enough to create vast numbers of matter and antimatter particles continuously. As the universe expanded and cooled, these particles annihilated with one another. For matter to survive, there had to be a slight imbalance from the very beginning, favoring matter by a tiny fraction. Understanding how this imbalance arose is known as the problem of baryon asymmetry. In principle, the laws of physics treat matter and antimatter almost symmetrically. Many fundamental interactions behave nearly the same when particles are replaced with their antiparticles. This symmetry suggests that the universe should not naturally favor one over the other. However, experiments in particle physics have revealed subtle violations of these symmetries. Certain processes involving subatomic particles do not treat matter and antimatter in exactly the same way. These violations are real, measurable, and essential clues. Despite this, the known symmetry violations appear too weak to explain the observed cosmic imbalance on their own. Calculations based on established particle physics fall short by a large margin. This suggests that additional processes must have operated in the early universe beyond what is currently included in the standard model of particle physics. Timing also plays a crucial role. The universe must have passed through conditions that allowed matter to gain a slight advantage before annihilation became dominant. These conditions are believed to have occurred when the universe was extremely young and energetic. At such times, particles behaved in ways that cannot be directly reproduced or observed today. Astrophysics must therefore rely on indirect evidence and theoretical consistency. One promising idea involves phase transitions in the early universe. As the universe cooled, it underwent transitions similar to how water freezes into ice. These transitions could have temporarily altered the behavior of fundamental forces in particles, creating environments where matter-antimatter symmetry was broken more strongly. If such processes occurred, they could have generated the small excess of matter needed to populate the universe. Another possibility is that entirely new particles or interactions existed in the early universe and later disappeared or became irrelevant. These hypothetical entities could have decayed in ways that favored matter over antimatter. While speculative, such ideas are motivated by the fact that the known laws of physics appear incomplete. Dark matter, neutrino masses, and cosmic acceleration all hint at physics beyond current models. Astrophysical observations provide important constraints on these ideas. The abundances of light elements, produced during the earliest stages of cosmic evolution, depends sensitively on the matter content of the universe. Measurements of these abundances match predictions only if the matter-antimatter imbalance had already been established very early on. This means the asymmetry is not a late-time phenomenon, but a foundational feature of the cosmos. The cosmic microwave background also encodes information about matter density in the early universe. Its detailed structure confirms that matter was present in sufficient quantities to seed the growth of galaxies. Without the primordial imbalance, these structures would never have formed. The smoothness and uniformity discussed in earlier chapters are compatible only with a universe where matter slightly outnumbered antimatter from the beginning. What makes this problem especially striking is how small the imbalance had to be. For every vast number of annihilating particle-antiparticle pairs, only a tiny residue of matter remained. That residue, multiplied across cosmic volume, became all stars, planets, and living beings. In this sense, the universe exists because of an almost perfect cancellation that was just imperfect enough. Despite decades of research, no single explanation has been confirmed. Laboratory experiments continue to probe matter-antimatter differences with increasing precision. Astrophysical observations search for any hint of antimatter on large scales. So far, all evidence points to a universe fundamentally biased toward matter, without revealing why that bias exists. This mystery connects deeply to other unresolved problems. It touches on the origin of physical laws, the behavior of particles at extreme energies, and the nature of time itself. Creating an imbalance requires not only asymmetry in physical interactions, but also a direction of time. In a perfectly time-symmetric universe, matter and antimatter would behave identically. The fact that time appears to flow in one direction may be intimately linked to why matter survived. The problem also highlights the limitations of extrapolating known physics into regimes far beyond experimental reach. Astrophysics often succeeds by extending well-tested theories to new contexts. Here, that approach seems insufficient. Something essential appears to be missing from our description of nature. Yet the very existence of the problem is a testament to how deeply we understand the universe. We can trace cosmic history back to moments when the difference between existence and non-existence hinged on subtle physical effects. We can quantify how much matter should have remained and compare that to what we observe today. Few sciences operate with such reach. As the universe expanded and cooled, the matter that survived began to form atoms, then stars and galaxies. Every structure owes its existence to that primordial imbalance. The absence of antimatter is not a trivial detail, but the reason there is a cosmos filled with complexity rather than a featureless sea of radiation. As you sit with this idea, it may feel both humbling and calming. Everything you know, including yourself, exists because the universe was slightly uneven at the very beginning. Perfect symmetry would have erased it all. Instead, a gentle imperfection allowed reality to unfold. As the day fades, you can let this thought soften into quiet reflection. Existence did not require grand excess, only the smallest imbalance. The universe did not choose abundance over emptiness by force, but by a whisper of difference. And just as matter quietly remained when annihilation ended, you can allow the noise of the day to fall away, leaving behind a simple presence, steady and at rest. Chapter 9. Is the universe finite or infinite? At first glance, the question of whether the universe is finite or infinite seems simple. Either space goes on forever, or it does not. Yet in astrophysics, this question unfolds into one of the most subtle and difficult problems we can ask. It touches geometry, observation, and the limits of what can ever be known. Unlike many cosmic mysteries, this one may not have a single definitive answer, not because of missing data, but because of how the universe itself is structured. When we look into the night sky, we see only a portion of the universe. Light travels at a finite speed, and the universe has a finite age. As a result, there is a boundary to how far we can see, known as the observable universe. This boundary is not an edge in space, but a limit in time. Beyond it, light has not had enough time to reach us. It is crucial to distinguish this observable region from the universe as a whole. The observable universe is finite by definition, but the total universe may extend far beyond it. Astrophysics can measure the size of the observable universe with great precision. It can map galaxies, background radiation, and large-scale structures across vast distances. Yet all such measurements are confined to what lies within our cosmic horizon. No telescope, no matter how powerful, can directly probe what lies beyond. This creates a fundamental challenge. The question of whether the universe is finite or infinite concerns the totality of space, not just the part we can see. To approach this problem, scientists study the geometry of space. According to general relativity, space can be curved by energy and matter. This curvature can be positive, negative, or zero. Each possibility corresponds to a different global structure. A universe with positive curvature would be finite, like the surface of a sphere, but without edges. One could travel indefinitely without ever encountering a boundary, yet the total area would be limited. A universe with zero or negative curvature could be infinite, extending without limit. Observations of cosmic background radiation provide powerful constraints on spatial curvature. The patterns of tiny temperature variations across the sky reveal how light has traveled through space over cosmic time. These measurements indicate that space is very close to flat on observable scales. Flatness, however, does not settle the question. A flat universe can still be finite or infinite, depending on its global topology. Topology describes how space is connected on the largest scales. Even a universe that appears flat and uniform locally could wrap around itself in complex ways. In such a universe, traveling far enough in one direction might eventually bring you back to your starting point, much like moving across the surface of a cylinder or torus. Detecting such global properties would require observing repeating patterns across the sky, such as identical structures appearing in different directions. Extensive searches for such patterns have so far found no convincing evidence. But the absence of evidence is not evidence of absence. The universe could be much larger than the observable region, hiding any repetitions beyond our reach. Another layer of complexity comes from cosmic expansion. Space itself is expanding, carrying galaxies apart. This expansion does not imply that the universe is expanding into something else. There is no external space into which the universe grows. Expansion describes how distances within space increase over time. Whether the total amount of space is finite or infinite is a separate question from whether it is expanding. If the universe is infinite, it presents conceptual challenges. An infinite universe would contain infinitely many regions like our own, including infinitely many galaxies and potentially infinitely many configurations of matter. This leads to paradoxes and philosophical discomfort, but not necessarily physical inconsistency. Physics can describe infinite systems, even if human intuition struggles with them. If the universe is finite, it raises different questions. What determines its size and shape? Why does it have that particular global structure rather than another? Finite does not mean bounded by walls or edges. In most physically realistic models, a finite universe has no boundary one could encounter. Space simply loops back on itself. This idea can be difficult to visualize, but it is mathematically consistent and compatible with known laws. Importantly, astrophysics may never be able to distinguish conclusively between these possibilities. The universe could be finite, but so large that its curvature and topology are undetectable within the observable region. It could be infinite, but appear finite to us because of observational limits. In both cases, all measurable quantities within our horizon would look nearly identical. There is also the question of whether infinity is physically meaningful or merely a mathematical abstraction. Some physicists suspect that truly infinite quantities may not exist in nature, serving instead as idealizations. Others argue that there is no compelling reason to exclude infinity from physical reality. At present, astrophysics offers no definitive guidance. The fate of the universe does not settle the question either. Whether expansion continues forever or changes behavior over time affects the future, not the total size. An infinite universe can expand forever, and a finite universe can also expand indefinitely without ever becoming infinite. Expansion changes distances, not topology. What makes this problem especially profound is that it reveals the boundary between empirical science and metaphysical speculation. Astrophysics thrives on observation and testable prediction. Here, it confronts a question that may lie beyond those tools. The universe may simply be too large, or structured in such a way that its total extent cannot be determined from within. This does not mean the question is meaningless. It shapes how we think about our place in the cosmos. In a finite universe, everything that exists is part of a single bounded whole. In an infinite universe, our region is one among endlessly many. Both possibilities are humbling, but in different ways. The history of science shows that questions once thought unanswerable sometimes yield to new methods. It is possible that future theories or observations will uncover subtle clues about the global structure of space. For now, however, the question remains open, not because of a lack of effort, but because of the nature of cosmic limits. As the universe evolves, regions beyond our horizon recede further, never to be observed. In this sense, the accessible universe becomes effectively smaller over time, even as space expands. The question of infinity becomes less about physical reach and more about conceptual understanding. As you reflect on this, it may be comforting to recognize that finitude and infinity need not be resolved to give meaning to experience. Whether space is endless or closed, your presence occupies a finite moment, a local pocket of awareness in a vast structure. As the day winds down, you can let this question rest without urgency. The universe does not require you to grasp its total extent. It simply unfolds, whether bounded or unbounded, carrying you gently within it. You can release the need to know how far it goes and allow yourself to be exactly where you are, here, now, at peace within a cosmos that is vast enough to hold both mystery and rest. Chapter 10. Are there limits to what astrophysics can ever know? Astrophysics is often associated with discovery, expansion of knowledge, and the steady illumination of the unknown. Over the past century, it has transformed humanity's understanding of the universe, revealing galaxies beyond our own, uncovering the expansion of space, and identifying exotic objects such as neutron stars and black holes. Yet alongside these successes emerges a quieter and more profound question. Are there limits to what astrophysics can ever know? This is not a question of temporary ignorance or technological delay, but of fundamental boundaries imposed by the structure of the universe and the laws of physics themselves. At its core, astrophysics is an observational science. It depends on signals that reach us across space and time, primarily in the form of light, particles, and gravitational waves. Everything we know about the universe beyond Earth comes from interpreting these messengers. This reliance immediately introduces limits. Signals travel at finite speeds, and the universe has a finite age. As a result, there are regions of space from which information can never reach us, no matter how advanced our instruments become. The concept of a cosmic horizon captures this idea. There are parts of the universe that are permanently beyond observational access, not because they are hidden or obscured, but because space itself expands in such a way that light from those regions will never arrive. This horizon is not a practical limitation that future technology might overcome. It is a fundamental feature of cosmic geometry. Astrophysics can describe the existence of such horizons, but it cannot see past them. This immediately places a boundary on cosmological knowledge. We can measure the observable universe with extraordinary precision, but we cannot directly determine the properties of regions beyond it. Whether the universe extends infinitely or has a finite global structure may never be settled conclusively. Any answer must rely on inference rather than direct evidence, and some inferences may remain forever ambiguous. Limits also arise from the nature of physical law. Many of the most successful theories in astrophysics are effective descriptions rather than ultimate ones. General relativity describes gravity and space-time with remarkable accuracy across a wide range of conditions. Quantum theory describes the behavior of matter and energy at small scales with equally impressive success. Yet when these theories are pushed to extremes, such as the interiors of black holes or the earliest moments of cosmic history, they cease to provide clear answers. This breakdown suggests that there are domains where our current theoretical frameworks are incomplete. Even if a deeper theory eventually unifies gravity and quantum physics, it may introduce new limits rather than removing old ones. Some proposed frameworks imply that space-time itself has a minimum scale, below which the concept of distance loses meaning. Others suggest that certain quantities cannot be measured with arbitrary precision, not because of experimental imperfections, but because nature forbids it. In such cases, uncertainty is not a temporary obstacle, but a built-in feature of reality. Another fundamental limit arises from the role of information. Astrophysics relies on extracting information from distant systems, but information is constrained by physical laws. There are limits to how much information can be stored, transmitted, or retrieved from a given region of space. Black holes, for example, appear to place absolute bounds on information density. These bounds imply that the universe may not allow arbitrarily detailed descriptions of all its parts. Time also imposes constraints. Many astrophysical processes unfold over immense durations, far exceeding human lifespans or even the expected lifetime of our civilization. Some phenomena may be so slow that their full behavior can never be observed directly. Others may have occurred only once in the deep past, leaving behind incomplete traces. The origin of the universe is a prime example. We can observe the aftermath, but the event itself may never be fully reconstructed. There's also the problem of initial conditions. Astrophysics excels at describing how systems evolve given certain starting points. It struggles when asked why those starting points existed at all. This limitation appears repeatedly, whether in cosmology, stellar formation, or planetary systems. At some level, explanation gives way to description, and description gives way to silence. Importantly, these limits do not arise from a failure of scientific method. They emerge precisely because the method is applied rigorously. Astrophysics does not claim access to absolute truth. It builds models that can be tested against observation and revised when necessary. When observation itself becomes impossible, the discipline honestly acknowledges that boundary. There is also a distinction between what is unknown and what may be unknowable. Many open problems in astrophysics fall into the former category. Dark matter, dark energy, and the details of galaxy formation may eventually be understood through improved observations and theories. Other questions may belong to the latter category, constrained by horizons, causality, or the structure of physical law. Distinguishing between these categories is itself an ongoing challenge. Some philosophers of science argue that limits to knowledge are inevitable in any sufficiently complex system. A theory that describes the entire universe from within the universe may encounter self-referential constraints. An observer embedded in a system cannot always fully characterize that system. This idea echoes across disciplines, from mathematics to computation, and may apply equally to cosmology. Astrophysics also faces limits of interpretation. Observations do not speak for themselves. They must be understood through theoretical frameworks that guide their meaning. When multiple frameworks explain the same data equally well, choosing between them becomes difficult. This situation already arises in several areas of cosmology, where different models fit observations with comparable accuracy. In such cases, knowledge becomes probabilistic rather than definitive. Despite these constraints, it would be a mistake to view limits as failures. Boundaries define the shape of understanding. Knowing where explanation ends is itself a form of knowledge. It clarifies what questions are meaningful, what answers are provisional, and where humility is required. The history of astrophysics shows a continual pattern of pushing limits outward. What was once thought unknowable, such as the existence of other galaxies or the composition of stars, later became well understood. This history cautions against declaring any current limit final. At the same time, it also teaches that some boundaries persist, reappearing in new forms even as others recede. There is a quiet balance in this tension. Astrophysics advances by confronting mystery, yet it remains grounded in what can be tested and observed. It neither promises total comprehension nor resigns itself to ignorance. Instead, it operates within a landscape shaped by both discovery and restraint. Ultimately, the question of limits is also a question about expectation. Do we demand that the universe be fully transparent to human inquiry, or do we accept that some aspects may remain forever beyond reach? Astrophysics suggests the latter. The universe appears intelligible enough to study, yet vast enough to resist complete capture by any single mind or theory. As you reflect on this, there is no need to feel diminished by these limits. They do not imply that understanding is fragile or incomplete in a discouraging sense. They simply indicate that the universe is larger than our need to master it. As the day comes to a close, you can allow this thought to settle gently. You do not have to carry the weight of every unanswered question. The universe continues with or without full explanation, and so do you. Knowledge has edges, but rest does not require crossing them. You can let the questions remain open, floating quietly at the boundaries of thought, while your mind eases into stillness, content within a cosmos that allows both curiosity and calm. You made it all the way here, and I'm really glad you stayed with me. If you're still awake, there's another quiet journey waiting for you on the channel. Another story about space, time, and the universe, told slowly and gently. And if sleep is already close, that's perfect too. May your thoughts fade into starlight, and may you drift into sweet dreams among the stars.